This talk is about the square root of -1. But trying to take the square root of a negative number doesn't seem to make any sense. After all, 1 times 1 is 1, and -1 times -1 is also 1. So what is the square root of -1? And more generally, what are complex numbers and how did they arise? How do we calculate with them and how do we picture them? And can they be generalized in any way? These mysterious objects caused uncertainty for many centuries. In the 17th century, Gottfried Leibniz had been enthusiastic, claiming that the imaginary numbers are a wonderful flight of God's spirit. They are almost an amphibian between being and not being. But a century later, the Victorian Augustus de Morgan complained that we have shown the square root of -a to be void of meaning, or rather self-contradictory and absurd, while his contemporary, the astronomer George Airy, said, I have not the smallest confidence in any result which is essentially obtained by the use of imaginary symbols. Somewhat surprisingly, the Swiss mathematician Euler, who later contributed so much to their development and use, had been even more critical, saying that all such expressions, such as the square root of -1, the square root of -2, etc., are impossible or imaginary numbers, since they represent roots of negative quantities. And of such numbers we may truly say that they are neither nothing, nor greater than nothing, nor less than nothing, which necessarily makes them imaginary or impossible. However, he did admit that nothing prevents us from making use of these imaginary numbers and employing them in calculations. And eventually he came to accept the square root of -1, writing it as I, the first letter of imaginary. Here's the very first appearance of I in print, in a book he wrote on the integral calculus, published in 1784. But square roots of negative quantities had already arisen some 2,000 years ago in a problem on pyramids. Heron of Alexandria was attempting to find the height h of a truncated square pyramid, one with its top chopped off, where the side length A of the bottom square was 28, the side length B of the top square was 4, and the length C of each slanting side was 15. To do so, he used the formula on the right to calculate the height, clearly unaware that an object with these dimensions cannot exist. And he found h squared to be -63, so that the height is the square root of this. Realizing that this made no sense, he fudged the issue by presenting his answer simply as the square root of 63. More successfully, 1500 years later, the Italian polymath Cardano wrote a classic text, The Great Art, in which he posed and solved problems that involved algebra. One of these problems was to divide 10 into two parts whose product is 40. Calling these parts x and 10 minus x, which certainly add up to 10, he obtained the quadratic equation x times 10 minus x equals 40, which can be rewritten as x squared minus 10x plus 40 equals 0. Solving this equation then led to the solutions x equals 5 plus the square root of -15 and x equals 5 minus the square root of -15, which seemed meaningless. But he struggled on regardless, writing, nevertheless, we will operate putting aside the mental tortures involved. And after checking that the sum of these solutions is 10, and that their product is indeed 40, he concluded, so progresses arithmetic subtlety, the end of which is as refined as it is useless. For many purposes, our ordinary real numbers are all we need. But suppose we do agree to allow this mysterious object called the square root of minus 1, or I, where I squared equals minus 1. Ignoring what it actually means, we can then form many more numbers, such as 1 plus 3i and 2 plus I. We call these complex numbers, a name given them by the 19th century German mathematician Carl Friedrich Gauss. We can then carry out some simple calculations with them. Adding is straightforward. We just add the bits without the I and the bits with the I separately. So that here, 1 plus 3i added to 2 plus I is 1 plus 2, that's 3, plus 3i plus I, that's 4i, giving 3 plus 4i. And subtraction is equally simple. Multiplication is also straightforward, as long as we remember to replace I squared wherever it appears by minus 1. So A plus BI times C plus DI is AC plus ADI plus BCI plus BDI squared. And replacing I squared by minus 1 gives AC minus BD plus AD plus BC times I. For example, 1 plus 3i times 2 plus I is 2 plus 3i squared, that's 2 minus 3, plus I plus 6i, giving minus 1 plus 7i. How can we visualize these complex numbers? Representing them geometrically was first done by Caspar Wessel of Norway in 1799, and later by Carl Gauss of Germany and Jean-Robert Argand of France. The result is often called the Gaussian plane or Argand diagram, but neither name is historically correct, and it's much better to call it the complex plane. We represent each complex number a plus bi by the point of the plane with coordinates a, b. And the picture on the left shows 4 points represented in this way: 1 plus 2i, 3 plus I, minus 2 plus I, and 3 minus 2i. We can then add two complex numbers by using the so-called parallelogram rule, as illustrated on the right, where 1 plus 3i plus 2 plus I is the point at the top corner of the parallelogram, which is 3 plus 4i as before. One interesting feature is that multiplying a complex number by I corresponds to rotating it anti-clockwise through 90 degrees. For example, as we've shown on the left, multiplying the complex number 3 plus 2i by I rotates it through 90 degrees to I times 3 plus 2i, which is minus 2 plus 3i. And if we then multiply this by I, we rotate through another 90 degrees, as pictured on the right. So multiplying by I squared, which is minus 1, rotates 3 plus 2i through 180 degrees, giving its negative, which is minus 3 minus 2i. Let's now look at some equations from algebra. Some have real number solutions. For example, the equation x squared equals 1 has the two solutions x equals 1 and x equals minus 1. But others do not. For example, the equation x squared equals minus 1 has the imaginary solutions x equals I and x equals minus I. To explore this idea further, let's look at the three quadratic equations on the left. To solve the equation x squared minus 4x plus 3 equals 0, we can factorize the left-hand side directly as x minus 1 times x minus 3. So either x minus 1 is 0 or x minus 3 is 0, giving x equals 1 or 3. So there are two real solutions. For the second equation, x squared minus 4x plus 4 equals 0, we can again factorise the left-hand side, this time as x minus 2 all squared. So we have one real solution, x equals 2, but repeated. But for the third equation, x squared minus 4x plus 5 equals 0, we need to introduce I. Here, the left-hand side factorises as x minus 2 minus I times x minus 2 plus I, giving x equals 2 plus I and x equals 2 minus I, two complex solutions. If we now look at the graphs of these three equations on the right, we see that the first one, y equals x squared minus 4x plus 3, crosses the x-axis when x is 1 and x is 3, the two solutions. The second one, y equals x squared minus 4x plus 4, just touches the x-axis when x is 2, the repeated solution. And the third one, y equals x squared minus 4x plus 5, with complex solutions, misses the x-axis altogether. In this last case, the two solutions are imaginary. They're there, but you can't see them. As we've seen, there was much suspicion in Victorian times about these imaginary numbers. Based on representing complex numbers as points in a plane, the Irish mathematician and astronomer William Rowan Hamilton largely ended this suspicion by defining complex numbers a plus bi to be pairs ab of real numbers, which combine according to the particular rules shown here. These rules correspond to the ones we used for adding and multiplying complex numbers. Here, the pair 0, 1 represents I, and the equation 0, 1 times 0, 1 equals minus 1, 0 is just the equation I times I equals minus 1. So because complex numbers correspond to points in a plane, a natural question is to ask whether there's a similar correspondence in 3 dimensions, based on numbers of the form a plus bi plus cj, where I squared and j squared are both minus 1. Addition still works, but multiplication does not, because of the product I times j that arises when you try. Hamilton tried many ways to deal with this difficulty, but they all failed. As he later wrote to one of his sons, "Every morning on my coming down to breakfast, your brother William Edwin and yourself used to ask me, 'Well, Papa, can you multiply triplets?' Whereto I was always obliged to reply with a sad shake of the head, 'No, I can only add and subtract them.'" After struggling with these troublesome triplets for many years, Hamilton had his moment of glory on the 16th of October 1843, during a walk with his wife along Dublin's Royal Canal. As he recalled, "As I was walking with Lady Hamilton to Dublin and came up to Broome Bridge, I then and there felt the galvanic circuit of thought close, and the sparks which fell from it were the fundamental equations exactly as I have used them ever since. I pulled out on the spot a pocket-book and made an entry. It is fair to say that this was because I felt a problem to have been at that moment solved, an intellectual want relieved which had haunted me for at least 15 years since." So what was this wonderful solution? What Hamilton had discovered were his quaternions. These have the form a plus bi plus cj plus dk, where a, b, c and d are all real numbers, I squared, j squared and k squared are all minus 1, and I times j times k is also minus 1. Addition is then as expected, but multiplication is no longer commutative in that ij is no longer equal to ji, but instead is equal to minus ji. jk is no longer kj, but is minus kj. And ki is no longer ik, but is minus ik. And as long as you stick to these rules, you can then multiply any two quaternions. Hamilton was so excited that he carved his equations on the bridge. It now bears a plaque shown here, which commemorates this discovery. Also pictured here are a page of his notebook and an Irish postage stamp that was issued to commemorate his achievement. Hamilton's quaternions have had many applications in geometry and physics. They can be used to represent rotations in 3 and 4 dimensions, and have arisen in many contexts, such as the tracking of satellites, film animation, and the theory of relativity. And with those exciting applications in mind, I thank you for listening.